Okay, so last time we finished with the treasure hunt puzzle. You find a note signed by a famous pirate, which is supposed to be a map that would lead you to a treasure, but as that pirate loves logical puzzle, instead he gave you 5 clues and told you that they are true and challenged you to use those clues to figure out where he buried the treasure. So let's see if you could figure out where is the gold. Here are the clues. First one, if this house is next to a lake, then the treasure is not in the kitchen. Second, if the tree in the front yard is an elm, then the treasure is in the kitchen. Third one, this house is next to a lake. Then the tree in the front yard is an elm or the treasure is buried under the flagpole. And finally, if the tree in the backyard is an oak, then the treasure is in the garage. So here are the statements that form those sentences. Those clues talk about 6 different things, each of which can be true or false. First, this house may or may not be next to the lake. The tree in the front may be an elm, maybe not. The tree in the back may or may not be an oak. The treasure could be in the kitchen, it could be under the flagpole, or it could be in the garage. Who knows, maybe he buried pieces of treasure in several places, but let's just assume for now that there is just one place that we could figure out, and if we cannot figure it out from here, then he probably didn't bother to put the treasure there. So notice that when we were translating the things that he talked about into propositional statement, we tried to go with the simplest possible one. For example, we didn't make B being the treasure is not in the kitchen, because it's an extra word. We want to keep things simple. So we just say the treasure is in the kitchen. Well, it may be true, may be false. So if we say it with those letters, we get something like this. And in the logic notation, here are our 5 clues. So far, with the method that we studied, your next step would be to go and start doing a truth table. But there are 6 possible variables here. So your truth table is getting to be sizable. A bit too long for my liking. Can we do it faster? Let's see how you would do it by just thinking about it. How you would solve this puzzle without, for a moment, thinking about logic. So here are your statements. Here are your clues. So what would be the first thing that you would do if you just were given the clues and you were trying to find the treasure? You would say, well, first of all, the third clue just says that the house is next to a lake. And, well, yeah, this house is next to the lake. And moreover, the pirates say that each of those 5 statements is true. The house must be next to the lake. Can we get something more out of the fact that the house is next to the lake? We know that if the house is next to the lake, then treasure is not in the kitchen. Well, since we do know that it is next to the lake, we can just go ahead and infer that the treasure is not in the kitchen. No use for digging out the floors. We learned something. We learned one place where the treasure is not. Can we actually figure out where the treasure is? Well, let's keep going. Now, we have one more statement that we didn't have before, the not B, that the treasure is not in the kitchen. Can we infer something new from the not B? Well, we do have the statement, if C is true, then B is true. If the tree in the front is elm, then the treasure is in the kitchen. But wait a moment, we know that the treasure is not in the kitchen. And if the tree in the front were elm, well, then the treasure would have to be in the kitchen. The tree in the front better not be elm. Don't we need to go looking for it? Besides, that tree must have been gone long time ago, or somebody changed it. Who knows? At least from those clues, we know that at the pirate's time, the tree would not be an elm. But this tells us something about the tree. It still doesn't tell us where the treasure is. Can we get something more? Well, we still have several clues that we never used. And one of them is either the tree in the front is an elm or the treasure is under the flagpole. But wait a moment, we know that the tree in front is not an elm. So the only way to make this statement true is to have the second part, the D, to be true. And what does D says? The D tells us that the treasure is under the flagpole. Great. We derive a statement that tells us where the treasure is. And here it is. It's under the flagpole. So when we were doing this, I put pretty much everything in words. I still use variable name, but I put it in words just because I wanted you to think about your own mental process. If I were faced with this problem, how would I solve it? What would I do first? What would I know right away? Where can I get in 1 step, in 2 steps, in 3 steps? Well, here in 3 steps, you could get to the treasure. Now you just need to dig it out. Now, I want to talk about how we could solve those things in general. What kind of rules do we use intuitively, at least when we know logic, to solve those kinds of puzzles? And what kind of rules we may try to use and then find out that the rule is not really quite the rule and it doesn't really work. So let's look at this. In logic, when we talk about an argument, we don't mean people fighting. We just mean that it's some kind of list of propositional statements, of formula. If the tree in the front yard is an elm, then the treasure is in the kitchen. That's a propositional statement. And here we have a list of them. Before, we always look at one formula at a time. Well, sometimes we were comparing two and saying whether they're equivalent or not, but here we are given a whole list of formulas. And we are trying to get something new out of that whole list. So what we are trying to get out of that list of formulas is called the conclusion. So the last statement in that sequence is called the conclusion. And all the rest are premises. So when we have a list of things, then we keep deriving something new and something new and something new until we get a sentence that says something about whatever we want to know. For example, in the puzzle case, we wanted a statement that says the treasure is here, under the flagpole, in the garage, in the kitchen. Getting each one of them to be true would solve our problem. Okay, so an argument is a sequence of propositional statements. That's a not very, how should I say, useful definition if you want to talk about things being true or false. What you really want to be talking about is whether the argument is valid. And an argument is valid is whenever all premises are true, the conclusion must also be true. So here's how you would say it. If you have premises P1 and so on and so forth, we had 5 of them in the treasure hunt puzzle, and you have a conclusion called C, like the treasure is under the flagpole, then the argument is valid if and only if it's the definition of being valid. Your sentence that says the first thing and second and all of them are true, and all premises are true, implies that the conclusion is true. This sentence is a tautology. That is, if you were to write the gigantic truth table for it, you would find that at every row of the truth table, every scenario, you get P1 and P2 and P3 and P4 and P5 implies conclusion. This must be true. The 5 clues imply that the treasure is under the flagpole. That must be true if our argument for figuring out where the treasure is was actually valid. So here the premises are the 5 clues, and the final conclusion is that the treasure is under the flagpole. And the whole thing is an argument. So we often write arguments in this format. We write the list of premises as a list, then we put a line underneath, and we put the strange symbol, which is the 3 dots, call it the therefore symbol, and then we put the statement of the conclusion. For example, if the house is next to the lake, then the treasure is not in the kitchen. The house is next to the lake, therefore the treasure is not in the kitchen. Here is a longer example. If x is greater than 3, then x is greater than 2. Well, duh. If x is greater than 2, then x is not equal to 1. That also makes sense. And also, x is greater than 3. Therefore, we can infer that x is not equal to 1. It would take us more than one step to do it, as it took us more than one step to get that the treasure is under the flagpole, but this is a valid argument. If you take if x is greater than 3, then x is greater than 2, and if x is greater than 2, then x is not equal to 1, and x greater than 3 implies x not equal to 1, and write the truth table for it, you'll see that this is a tautology. So let's look at those 3 arguments. So the first one we already saw. It's a valid argument because we could prove that P implies Q. Our first thing, something next to lake, implies not in the kitchen. And P, the house next to the lake, the whole thing implies Q. That's a tautology. You could check it. And here I used variables to stand for kind of the general format of things mentioned in premises. Probably using formulas would be even better, but in this particular case it doesn't really matter. All I want to say is that if we write the outline of that argument, it will be a tautology. So in the second one, we have P implies Q, greater than 3 implies greater than 2. And we also have Q implies R, greater than 2 implies not equal to 1. And we also have the P, which is x greater than 3. And the whole thing implies R. Again, you could check that it's a tautology by doing the truth table. Okay, let's look at the slight variation of the second argument. Now suppose that you still know if it's greater than 3, greater than 2, it's greater than 2, then it's not equal to 1. And now I tell you that x is not equal to 1. And you say, oh, okay, great. I can say that x is greater than 3. But wait a moment. It could very well be that R is true, x is not equal to 1, but P and Q are both false. What if I set x to be a 0? It's not equal to 1, but it's definitely not greater than 2, and it's absolutely not greater than 3. So you could check that this is not a valid argument by just saying, wait a moment, there is a scenario, and that the scenario when R is true and P and Q are both false, where the whole thing becomes false, where the conclusion does not follow from premises. That means it's not a good argument. I wouldn't want to use it. So this style of argument is called the natural deduction. You have the clues, and you deduce the first thing, second thing, and you keep deducing stuff until you are done, until you get the answer. So how do we get the intermediate steps? Because we were saying the 5 clues imply that the treasure is under the flagpole, but we didn't just jump to the conclusion right away. Jumping to conclusion hardly ever works. We had those intermediate steps. And the way we get intermediate steps is something called rules of inference. Those are the rules based on those very simple tautologies which tell you that if you have your premises in a certain form, then you could derive things from them. So just like when we were studying equivalences, we said it's nice to simplify things so that we wouldn't need to write truth table or write the smaller truth table. We can apply tautologies to get some kind of intermediate sentences, and then we build more and more and more of those intermediate premises until we get the final conclusion. So here was one thing that we did. If the house is next to the lake, then the treasure is not in the kitchen, and the house is next to the lake, therefore the treasure is not in the kitchen. So here is where we apply the tautology. If P implies Q and P, we can infer that Q must be true. Or I should say P implies Q and P implies Q is a tautology. So if we know that P implies Q and we know that P is true, then we can infer that Q must be true as well. This is a special kind of tautology, probably the most famous rule of inference, which is known as modus ponens from Latin. And this is probably the main rule of inference that you would be using in solving those kinds of problems. And all it is applying the structure. If you have something implies something and you know the first thing, then you can infer the second thing. This stuff goes back to ancient Greece and to Aristotle and such, who has this famous syllogism, which in a simplified form, you'll see the full form a little bit later, says, if Socrates is a man, then Socrates is mortal, and Socrates is a man, therefore Socrates is mortal. And let's do something a bit more mathematical. If x is greater than 2, then x is not equal to 1. That's true. Let's take that x greater than 2 is true. Then we can infer that x is not equal to 1 in one single step given by this useful rule, useful tautology called modus ponens. So there are several variants of modus ponens, which other logicians would tell you, no, they're not variants of modus ponens. They're completely different rules of inference. But you know what? To me, they look just too similar. So I'll just call it friends of modus ponens. If you're looking up stuff on the web or in a textbook, they will have different names. And I'm giving you the names. But really, if you look at them, all of them are of the form, you know that P is true. And you know that P implies Q. Or maybe you know the contrapositive of P implies Q, which, as we just talked, is not Q implies not P. That's something equivalent. Or maybe you take the P implies Q and say, oh no, the implication. I hate implication because they're so confusing in English. Let me just write it in a simpler, more computer sciencey way as not P or Q. That's exactly the same statement. P implies Q, not Q implies not P or Q. They're all equivalent. And from all of them, if you know P, you could derive Q. So if somebody asks you what modus ponens is, please tell them that it's that first thing, P implies Q, P, therefore Q. But really, when you're solving those problems, you could think about the second and the third rule as applying modus ponens to the contrapositive of your statement or to the disjunction that you made by opening up the implication. So there is another kind of rule, which is slightly different but also useful, that we will look at a lot more soon. This is much more computer programming friendly rule. And that's the rule called resolution, and its friend that's called in the book the hypothetical syllogism. Here's how it works. The hypothetical syllogism says if P implies Q and if Q implies R, then P must imply R. If today is Monday, then we have a lecture. If we have a lecture, then I have to be at MON. If today is Monday, then I have to be at MON. So you see here, you don't derive one single thing, and you don't assume one single thing. You have an implication two implications as a premises and an implication as your conclusion. If you want to open up the implication and make things less confusing, you could write it as not P or Q. Either today is not a Monday or I have a class. Either I don't have a class or I have to be at MON. So either today is not Monday or I have to be at MON. It's exactly the same thing because not P or Q is equivalent to P implies Q and so on. So here is an example of applying this rule, the resolution hypothetical syllogism. If x is greater than 3, then x is greater than 2. If x is greater than 2, then x is greater than 1. And now I don't tell you stuff like, okay, x is equal to 0, or x is, I should really tell you something like either x is greater than 3 or x is not greater than 1, but instead, without me telling you anything else, you could conclude right away that if x is greater than 3, then in particular x is greater than 1. It's kind of common sense. So speaking of common sense, there are several more rules that you may come across which they kind of have names, but it's not really very famous name. They're kind of common sense rules, auxiliary rules. For example, if you've derived that P must be true from premises, if premises are true, then P must be true. And if premises are true, then a Q must be true. Then you know what you derive both. So from knowing that P is true and knowing that Q is true, you can conclude that P and Q are true. If you derive both, then you could just write it. So again, it's not really something fancy, just common sense. Here is a kind of an opposite rule. If you've derived that P and Q are both true, well, in particular, that tells you that P must be true. If you know both that the tree in the front is elm and that the treasure is not in the kitchen, well, in particular, I know the tree in the front is elm. And the third rule tells you that if you know P, then you could make any sentence P or something and it would still be true, just because remember, true or anything must be true. So if you derive that the treasure is not in the kitchen, then sure, you could say, oh yes, that means the treasure is not in the kitchen or the treasure is under the flagstone. No problem. Because you already know that this would be true just because of the first part of it. So this is pretty much all for the rules. If you go to other textbooks, especially philosophy textbooks and other mathematical textbooks, you may come across other rules with all sorts of different names and all sorts of variations. But really, I would say as long as you know modus ponens and say resolution and can do those little auxiliary things, like if I know both P and Q, then I know P and Q, then you could solve pretty much any problem. And here we are not really focusing on names, so the only two names that I would ask you to remember, because I will be using them a lot, would be modus ponens and resolution. So let me just say one more thing about proofs and disproofs. Because we started talking about arguments and how would you prove that your conclusion is true from premises. But a lot of time what you want to do is disprove a statement as opposed to prove it. So how would you do it? And how would giving a proof avoid being able to disprove stuff? You wouldn't want to prove and disprove stuff at the same time. So suppose somebody tells you, this is a tautology, this must be true, those premises imply this conclusion. This list of observations implies that whatever, something strange, that the earth is flat. What would you do with the statement? So to disprove that it's always true, it's enough to give just one scenario where it's false. Just find the falsifying assignment. For example, if somebody tells you, but wait a moment, I don't see why converse is not the same as an implication. Then you say, okay, let me disprove your statement that A implies B is equivalent to B implies A. Here is my counterexample. Take A being true and B being false. Then one side of this equivalence is true, another side of this equivalence is false. They cannot be the same. So this comes up a lot. If you need to prove, usually you need to go through different steps, infer stuff. If you need to disprove something, you just need to find one counterexample. So, for example, if you say, oh, I have classes every day, it's enough for me to say, well, wait a moment, do you have a class on Saturday? No? Well, you know what, then you don't have classes every day. You can surely have classes Monday to Friday. You can even have a class on Sunday. But as long as I can point to one day when you don't have classes, I disproved that I have classes every day statement. And here is another one that comes up a lot if you're like me. You do computer science? I thought girls don't do computer science. And I'm like, well, wait a moment. Didn't I just disprove this statement by my very existence? It's very easy to disprove stuff if you could find a counterexample. So here is another thing with proofs and disproofs. An argument is valid just means that if you assume that your premises are true, then your conclusion must be true. It's just that your premises imply your conclusion. But a lot of time, it's not that people's arguments are not valid. It's that their premises are somehow flawed. Here is an example what you could do when you have an argument that starts with premises that are false. A famous logician, Bertrand Russell, once was told, well, if you think that false implies anything, prove to me that if 2 + 2 = 5, then I'm the Pope. Well, Bertrand Russell thought about it and said, yeah, sure, here is a proof. Next time, I'll talk about this proof, but for now, think about it and see if you could figure it out yourself. How would you prove that if 2 + 2 = 5, then I'm the Pope?